In this section, we're going to be taking a critical look at human water usage, what types of human activities demand the most water, and how that is affecting global freshwater supply. Fresh water is an important sustainability issue because humans put a significant strain on the freshwater resources that are available on our planet. The demand for water by humans is also exacerbated by changing climate conditions that are being brought about. um, Drought and water scarcity conditions in many regions, including our own. This is a satellite time lapse that you saw previously in Chapter 1 on Arizona's largest lake, Lake Powell, between 1991 and 2015. And you can see how the lake has been drying up. On top of that, human demand for fresh water is going to continue to increase in future years. Because the world population is continuing to grow and population and people will require fresh water to serve their domestic needs. The growing world population will also need to be fed, and growing food takes a lot of water. In fact, 70% of freshwater withdrawals worldwide are used for agriculture. And finally, much of the population growth is slated to take place in countries that are developing and in the process of industrializing. And with that process comes a shift that we are already noticing to a diet that includes more meat and dairy products. And meat and dairy products are more water intensive to produce than plant foods because they're another step up the food chain. We are going to come back to the issue of water scarcity later in this section, but first we're going to look at water use in the US and in Arizona, including what that water use has looked like in the past and what it looks like today. In the country as a whole, demand for fresh water increased steadily in conjunction with the growing population between 1950 and 1980. In this figure, what you see is the total US population represented by the red line, and the bars represent freshwater withdrawals. The white bar is the amount of groundwater being withdrawn, the blue is the amount of surface water being withdrawn, and the black bar is the total. So you can see the population keeps going up, but at some point the water withdrawals stabilize and then later they even drop. So why did this happen? Well, you'll remember me saying just a moment ago that agriculture accounts for 70% of water usage worldwide. In the US today, agriculture is actually a close second to the thermoelectric power sector in terms of water usage, but agriculture is still a huge driver of water consumption. And the years between 1950 to 1980 were the height of the Green Revolution. Agriculture was expanding into newer regions, drier regions that didn't have the rainfall to support cropland, but were relying on irrigation. In this graph, you can see the number of irrigated acres in the US shown in the black line. And you can see a sharp upward trend in the number of irrigated acres between 1940 and 1990. After that, things kind of stabilize. But the other thing that you'll notice is that the line shown in red represents the water use per irrigated acre. In other words, how much water is being applied to an acre of cropland on average. And this line starts going down and has continued to trend downward as more farmers and agricultural operations adopt more efficient irrigation practices, like drip irrigation or sprinkler irrigation, which deliver the water to plants in a more precise way compared to traditional irrigation approaches that involved flooding the entire field. So the number of acres of irrigated cropland stopped going up so sharply, and people got more efficient about how they delivered their irrigation water, resulting in a stabilization of freshwater withdrawals. The other thing that happened is that the thermoelectric power sector started using less water. So this is water that is used to cool power plants and generating stations. In this figure, the yellow bar is the one that shows water withdrawals from thermoelectric power purposes. And you can see how it has dropped steadily from the year 2005 onward. This is because there has been a shift away from coal power plants and toward natural gas as a fuel source, as well as power plants becoming more efficient about the way they use their water. For example, just in the 4 year period between 2015 and 2019, power plants in the US used 20% less water to produce the same amount of energy because they were using the water more efficiently. However, the thing about a thermoelectric power water usage is that it is almost entirely non consumptive use. Remember, non consumptive use is when water is removed from a source but then returned back to the source after it is used. So, because the thermoelectric power sector uses water for cooling, that water will get pulled out of its source like a river. For example, be used to cool the nuclear reactor or whatever component of the power plant it's needed for, and then returned to the river. So, really, that water is not actually used up. Consumptive water use is the type of water use when the water is removed from the source and does not get put back. So, knowing this, if we look at total water in the United States, thermoelectric is up there with irrigation. Thermoelectric is shown in navy blue, irrigation is shown in yellow, and these are billions of gallons of water used per day. And to be clear, these numbers are actually somewhat outdated. They come from the year 1990, but the US Geological Survey hasn't published any data on total versus consumptive water use since 1990. They are currently preparing a report on the period between 2000 and 2020, but it hasn't been released yet. So, if we want to compare total water use versus consumptive use, we have to use the 1990 data for now. And looking at that data, thermoelectric rivals irrigation in terms of total water use. But remember that thermoelectric uses water non consumptively. If we look at consumptive use, irrigation takes over. The agriculture sector is by far the most significant use of water in a consumptive manner, meaning this water does not get returned to the source. 77 billion gallons every single day are used for agricultural irrigation in the US. So, this gives you an idea of how agriculture puts pressure on our freshwater resources. But of course, we are not trying to villainize agriculture. We have to be mindful of the fact that ultimately the purpose of growing crops is to feed people, to produce calories that can provide nutrition. And in this regard, not all sources of nutrition are equal in terms of their water consumption. This provides a breakdown of how many liters of blue water are required to produce a calorie of energy from these different food source types. Fruit uses a lot of water because it has a high water content and not a lot of calories in general. Milk, eggs, and red meat are also high because in order to raise cows for milk and meat or raise chickens, you first have to grow the crops to create their feed. So it's sort of like the biomagnification phenomenon we previously talked about. As you move up the food chain, the amount of water required to support that organism becomes more concentrated. You don't just have to consider the water that the cow drinks, but all the water that it was used to grow the crops that are being used to feed the cow. But the really interesting one is nuts. Nuts require a higher investment of blue water per calorie than any other category of food. A number that puts this in perspective is the fact that in California, almonds alone use 17% of all agricultural water usage. There are over 400 different crops grown in California, and just almonds, only one type of nut, uses 17% of the agricultural water. So raising nuts is a very water inefficient process. We can also look at calories sourced from different types of nutritional molecules. For example, this graph shows the amount liters of blue water required to produce not just any calorie, but a calorie of protein specifically. Why? It's an essential source of nutrition that your body needs. Fruits, again, are very high because there's very little protein in fruit, and they have a very high water content. But then again, we have nuts showing up, with over 20 liters of water being required to produce a single calorie of protein in the form of nuts. Even with a food chain effect that occurs with food sources like milk, eggs, and red meat, nuts are still far less water efficient at delivering protein to your diet. The most water efficient source of protein is legumes, which includes beans and peas. Final important lens for viewing water consumption in the US is patterns of consumption by region. In this figure, the dots of different colors correspond to water consumption sector. So yellow is thermoelectric, green is irrigation, blue is public supply like domestic and municipal, red is industrial, and gray is other. As you can see, water withdrawals in the west are primarily dedicated to irrigation because there is a lot of cropland in this region, but also relatively less water compared to the east. Whereas in the east, the primary driver of water withdrawals is thermoelectric power. There's a lot more going on in this image too. And so I encourage you to pause the video and read more detail in the text of the image if you're interested in more of the nuances of how water use varies around the country. Final topic that we'll touch on before closing on this section of water use is water scarcity. Water scarcity is the term used to describe situations where the need for water surpasses the available supply. And there are two types of water scarcity. The first is physical scarcity, which is where not enough water exists to meet the demands of a region. The Southwest US is an example of a region that is headed in the direction of physical scarcity as drought conditions continue to erode our water supply and we continue to overdraw our aquifers. The other type is economic scarcity. This is when enough fresh water exists and is available to meet a region's needs, but the infrastructure to treat the water and make it safe to use or to supply it to people does not exist. Because even regions that have abundant amounts of water can experience scarcity if they don't have water treatment plants, water line systems, sewage systems, and all of the other infrastructure needed to maintain a stable supply of safe water. Economic scarcity is primarily experienced by people in developing nations that are still in the process of industrializing. Because these nations often lack the resources to invest in some of the most effective approaches to minimize water scarcity, which include more efficient methods of agricultural irrigation, transitioning to more water efficient appliances, building water storage infrastructure like dams and reservoirs that can stabilize the amount of water available year round rather than relying on seasonal ebbs and flows, and reducing water pollution by minimizing agricultural and industrial runoff of hazardous chemicals into water supply. In our next section, we will be taking a closer look at, at this last one as we get into water pollution and water quality.